I welcome you all to this broadband communication system practicals. To start, first of all, we'd like to let's see about the trainer kit that we have. So we have optical fiber transceiver kit. In short, we call it as OFT, optical fiber transceiver kit. Transceiver means it has got transmitter also and receivers also, both here in this particular trainer kit. So talking about this kit first, let's see a few details about this kit. So as we know that the entire optical fiber communication system is based on three primary components. First is called the optical source, which is governed by an optical LED. In this case, here we have two transmitters, LED1 which is operating at 850 nanometer and LED2 operating at 650 nanometer. So this 650 nanometer is a visible source and 850 nanometer is an invisible source. So we can use this source to generate the light signal, and we can launch that light into an optical fiber. So this is a transmitter section. At the receiver part, at the receiver section, we have two detectors. Receiver part is governed by the detector. So we can see that there is a PD1 and there is PD2. So photodetector 1 and photodetector 2. So this forms the receiver section. About the remaining part here, which will required in some other practicals also. You can see here, here there are 8 switches provided to have that 8-bit data transmit. We can see that there is SW0, SW1, SW2 up to SW7. So these are the 8 we can say buttons. Corresponding to that, we have 8 lamps are provided here, like L0 to L7. So this provision is necessary to ensure that the link is established when you connect the optical fiber in the kit. So corresponding to SW0, when I press SW0, it should glow L0 lamp. So once it happens, this confirms that the link is established between the transmitter and receiver. About the remaining practicals, we have several other provisions also here. We can see that voice coder, then marker generator, then Manchester coder. So these blocks are required in other practicals, like digital link formation, where you give the Manchester data at various points of this coded data format, which is available here. So both the like encoding and decoding is possible. So here is encoding part and decoding part is available here also. So we'll discuss this encoding and decoding at the time of digital link practical. So various parameters which are various we can say, and the points which are required, but not to be included here at the time of introduction here, simply because we'll see in detail at the time of that respective practical. While turning on the kit, let's now make it on. Backside, you can see that backside there is a power on button. So just switch on. So once you switch on, you can see that there is a reset button. Below that there are two LEDs, L8 and L9. Those are now in on condition. There is a power on button. The power on LED is there, so it is also on. So this ensures that this board, the OFT trainer, is in working condition. You can see that there is a switch here. There is switch 8, which is having two positions, digital and analog. So depending upon whether you are working in digital link transmission or analog link transmission, we can keep that switch as per the requirement. Now we have first of all, now we have already seen the basics of the optical fiber transceiver kit. Now let's see the first common procedure which is involved in almost all practicals. So that is to establish a link between the transmitter and receiver. So for that, we take this simple, you can see that this is simple optical fiber which is there in my hand. So which is 1 meter fiber, right? So this is the primary component of your OFC. So along with the optical source and optical detector. So now we would like to establish the link between the transmitter and receiver. So for that purpose, what I am doing now, we have this optical source which is at the transmitter side, which is, let's say, at 850 nanometer. So I'm going to connect one end of that fiber into that optical source. So just tighten that one end, and the other end of that fiber I'm going to connect to the optical detector, which is PD1. Now we have connect 1 meter fiber between LED1 and PD1. So you can see that this LED1 is forming the optical transmitter part, and the PD1 is forming the receiver part, and we have joined the transmitter and receiver with the help of the optical fiber, which is carrying that signal from the transmitter side to receiver side. So this is 1 meter fiber. So to how to ensure that the link is established between the transmitter and receiver, so there is a simple procedure for that, and this is common for almost all practicals, around 4 to 5 practicals. So for that, you can see that we have towards this side we have 8 switches, SW0 to SW7. So when we connect the fiber between the LED1 and PD1, so how to ensure that link is established? Suppose I have pressed SW0, so corresponding L0 should glue. So in this case SW0 is on, but L0 is not on, so link is not established. So for establishing the link, there is a gain control knob provided here, so you can just vary that gain control knob. And press reset button. Sometimes it takes time, sometimes it happens very quickly. So one should have the patience till that procedure gets completed and the link gets established between the LED1 and PD1. Now you can see that if I press SW0, the L0 lamp glows on, that LED glows on. So if I press SW1, then L1 gets on. If I press SW7, then L7 goes on. So this confirms that link is established. That means whatever signal, if you want to transmit, let's say from the transmitter side towards the receiver side with the help of optical fiber, it is possible that the link is established and the data or the information can be delivered from the transmitter side to receiver side with the help of optical fiber, which is connected between the transmitter and receiver. So this is the common procedure before starting almost any practical of the BCS. So whatever practicals which are based on this fiber trainer kit, we'll call it as optical fiber transceiver kit, not trainer, optical fiber transceiver kit. So today we are going to perform one simple practical which is called numerical aperture measurement. So for that purpose, we don't want to establish the link between the transmitter and receiver. It's a simple practical. So for that purpose, what we do is simply take the light from one of the optical source, which is called let's say in this case 650 nanometer as a visible source. So what I am doing now, this is a fiber. I'm connecting that fiber to one of the optical source, which is LED1, LED2, having a wavelength of 650 nanometer. So now you can see that, yeah. So you can see here the other end, from the other end the light comes out. So simply because this is a visible source operating at a wavelength of 650 nanometer. So this is an optical transmitter. With the help of LED, we have generated or that wavelength of 650 nanometer is obtained from the other end of the fiber. So this confirms that this source is working and the light is coming out of that fiber. So now what we are going to see here is the simple practical which is called numerical aperture measurement. Now let's see some of the like theory part related to this before going to the practical. So our title is estimation of numerical aperture of the given fiber. So given plastic fiber. So we'd like to calculate numerical aperture of the given fiber. So let's see some theoretical stuff before entering into the practical. Right. So we know the principle which is responsible for the light propagation inside the optical fiber. So we know that this optical fiber is basically a dielectric waveguide. Similar to a normal waveguide that we studied in RMT. So in this case, the light enters into the optical fiber. let's say this is the angle at which the light ray enters into the optical fiber. So we know that the fiber is composed of three elements, the central part of which is called as a core, which is having refractive index of n1, and surrounding the core there is a cladding, okay, having refractive index of n2. So as we already studied in class that refractive index of core is normally kept than cladding, because the purpose of core is to carry the most of the energy, light energy. Almost 99.99% of the light energy is confined in the core. So therefore refractive index of the core is kept more than the cladding. So now here, since this optical fiber is a dielectric waveguide, you can see that just like a rectangular waveguide. So once the light enters into the optical fiber, so it makes certain angle with the core axis. So the maximum angle at which the light ray enters into the optical fiber is called as the acceptance angle, that we studied in class also, in theory also. So this angle is called acceptance angle, and now at this ray of light is entering into the optical fiber. So this is your core part. So once the light enters into the optical fiber core part, it hits the upper part of that core wall, you can say, and gets reflected by the principle of total internal reflections that we studied, right? When the incoming ray of light, which makes the angle which is greater than the critical angle, the ray of light gets totally reflected in the same medium and does not go into the cladding part. So this principle is called total internal reflection. So this is the phenomena which is responsible for the light to travel inside the optical fiber. So such series of reflections takes place inside the optical fiber, and the light ray gets confined or it gets travel inside the optical fiber. So this is the basic principle that we say that how the light enters into the optical fiber. Now talking about the numerical aperture term, which we'd like to estimate here. That is the title. We have this numerical aperture calculation. So what is numerical aperture? It is basically indicates the light collecting ability of the fiber. So it is the amount of light that is, let's say, collected by the fiber. It is a dimensionless quantity. So it is simply dependent on the acceptance angle. So if acceptance angle is theta a, then sine of that acceptance angle is called numerical aperture. So sine of theta a, that's theoretically we can calculate the numerical aperture. So practically procedure is a little bit different. So for that purpose, what we can see that, you can see that there is a setup here for measuring the numerical aperture numerical aperture measurement. So this is a glass assembly which is there, and we have the plane surface, and on top of the side we can insert the fiber, and we'd like to see the projection or its wavefront on that plane surface. Okay, let's see now the procedure. So I have taken the fiber, 1 meter fiber, and I am taking this light from the optical source which is operating at 650 nanometer, which is the visible source from this OFT trainer kit, optical fiber transceiver kit. So now this light is already available. You can see that light is already available. So I'm just going to put this into the setup.
रिप्लेस कर चेंज कर देना କେତେ ଟର୍ମିନେଟ୍ ସେଟା ହେଇଟା କେଟା
Now you can see this is a projection of that light which is coming out of the fiber. We have taken on that plane surface. So you will get a pattern like a wavefront like a circle. So just I have to plot that pattern with the help of plain paper. So I can insert the plain paper over there, over that plane surface, and I can draw that plane pattern, that circular pattern which is let's say obtained for certain distance from the tip of the fiber. So I am just going to have draw 3 to 4 wavefronts, circular wavefronts on a plain paper, and later on.
Yes.
Now just you can see that there is a circular wavefront So I can just change the position of the fiber, and I can get at least 3 to 4 different plane wavefronts, sorry, circular wavefronts. So now suppose I have drawn these wavefronts on the plain paper. So let's see now the procedure to find the numerical aperture. So suppose this is the setup that we already talked about. This is now the circular wavefront that just we have seen. Okay, so it has got almost two diameters there. One is BC, another is DE. So I'm just looking to measure that BC and DE with the help of scale. Once we draw it on a plain paper, just I will measure that BC and DE. Okay, and after measuring BC and DE, you can see that now the observation table is there. Okay, so this is the observation table to find the numerical aperture. So we are looking for serial number, then X, D, and the numerical aperture and acceptance angle theta. So what is X and D? Let's see that. So okay, for the first reading, suppose for the first reading, that is circular wavefront that we obtained. Suppose the horizontal diameter is suppose BC. We can say here vertical diameter BC and horizontal diameter is DE. So we measure that using scale. BC is suppose 0.2 and D is 0.2. So I will calculate X. Practically formula is BC plus DE by 4. So just put the values of BC and D. So I get X equal to 0.1. So I can put that value of X as 0.1 here. Similarly, D is a distance between the tip of the fiber and that surface. So we can see that here. So tip of the fiber is here and the plane surface is here. So I will just use the scale to find the distance between the tip of the fiber and this plane surface. So that distance is D. So it is around 0.1. Okay, that will be calculated. Then the expression for calculating numerical aperture practically is Na equal to sin theta equal to x upon under root x square plus d square, where x is already calculated BC plus D by 4 and D is the distance between tip of the fiber and the plane surface. So I can put the values of those x and D and I can get the numerical aperture, which is roughly for this case 0.707. So same procedure I will do it for 3 more plane wavefronts like this, which we have drawn on the plane paper by changing the position of the fiber with respect to plane surface, and it is possible to find the numerical aperture for all these 3 cases. Like you can see that one more reading where we have taken new wavefront. BC is there, D is there, then we have calculated X by putting those values BC and D, then again numerical aperture by finding that distance between the tip of the fiber and the plane surface. So putting X and D, we get Na equal to 0.44. So with that we'll complete the observation table like this, calculating X, distance between the tip of the fiber and the plane surface for different wavefronts. And now using that expression of Na is equal to x upon under root x square plus d square, this expression we can compute the this table. So numerical apertures are obtained for every light projection that we have taken on the plane paper, and we already seen that Na equal to sin theta. Theta is called acceptance angle, so theta is sine inverse of Na. So we can do it here by taking sine inverse of Na. We can get theta, which is called acceptance angle. And after completing the observation table, you can see that we have calculated NS for different positions. So we can calculate average Na also. By taking the average of all these NS, we can calculate average numerical aperture for the given fiber. Plus we can calculate average acceptance angle for this fiber. So this is the required part that comes under this practical, which is the objective called as numeric aperture measurement of the fiber. So almost observation table, the calculations, the initial theoretical part we have seen. How the light travels inside the optical fiber is the important part that students should know. Then the terms like acceptance angle, the terms like numerical aperture, their expressions to calculate numerical aperture. Here practically we have used different expression. In theory we have already used in class different formulas to calculate Na, like under root n1 square minus n2 square, or Na equal to n1 root 2 delta. So these 2 expressions also students should remember, and they will solve some numericals also in class based on this topic. So at the end of this session, you will mention the conclusion, right, that Na is actually independent of the distance, because Na simply depends upon the core and cladding refractive index, and it is independent. Even if we get the different projections of light, So it hardly depends on the distance. Almost constant NA we get even if the position of the fiber is changed. So the refractive index N1 and N2 of the coherent cladding simply decides the numerical aperture. So that is the overall about the first practical, that is called numerical aperture.